reaction kinetics. This is chapter 11. Today we're going to cover section 2, which is reaction rates and concentration. So reminders, the OWL has your chapter 8 exam. I think you got the rest of the week to do that. And then there's 2 OWLs. There's the one for optional chapter 11 questions and then the required questions. You must get a 75% on the required questions in order to be able to take the test for chapter 11. So here's the outline. We are going to cover all these sections, and today we're going to just cover section 2, reaction rate and concentration. So, key concepts. This is all we're going to do. We're going to focus on determining what's called the rate law or the rate expression. What we're going to focus on today is what is called initial rate data, and we'll explain that a little bit in a second, exactly what that means. So, when you consider a reaction, concentration makes a difference. Okay, when you consider how fast a reaction is going to go, concentration is going to make a difference, the concentration of your reactants. So consider hydrogen peroxide. It decomposes. H2O2 decomposes to make water and oxygen. Now, when it's very, very pure, that reaction is very fast. If you've ever seen the elephant toothpaste demonstration, that's using a very high concentration, 30% hydrogen peroxide, and it goes aggressively fast. However, when it's diluted down, that's the stuff you actually use on cuts and such, it fizzes much, 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 much slower. So the concentration of the hydrogen peroxide dictates how fast the bubbles, the O2, and the water heat from the water bubbles form. So here's an example, shows you the hydrogen peroxide. The one on the left is with a slower concentration. The one on the right is a higher concentration. You can see when the one on the right really goes crazy, crazy fast because there's a much, much greater concentration of hydrogen peroxide. So why is that? Well, if you think about it, and this is in one of the videos that I shared with you yesterday, they talked about collisions. So in order for a reaction to take place, one really, really key concept has to happen. The molecules have to collide with one another, so they have to bang into one another. So when they bang into one another, and actually the video that I thought was kind of cute was the one where it talked about how the two people were walking or running in the halls, and they ran into one another, and they caused the collision so aggressive that their books went flying everywhere. So if you think about it, if you were in the halls and you're walking in the halls and you're walking along and you bump into somebody else, you're not going to suddenly spew forth and have your book go flying everywhere, because that wasn't an effective collision. You were not running very fast. They were not running very fast. You just happened to glance off one another. You didn't really hit where books were, blah, blah, blah. It didn't happen. But if you're in the halls with a lot of people, I mean a lot of people, and you're trying to get from point A to point B, it's very, very possible that someone's going to hit you in such a way that they're going to clip your books, especially if you're carrying them in your hands. Clip your books and make you have your books go flying. So the more people that are in the halls, the more likely that there's going to be a collision that's going to result in a reaction or an effective collision. So whatever we can do to increase the number of effective collisions, the more likely the reaction is going to take place. Well, one of the ways is with concentration. Add more people. Add more people are going to bang into you. The other thing that was mentioned in the video, which we'll address a little later on in another section, is temperature. Make those molecules move faster. Make those molecules move crazy faster, and there's more likely to have an effective collision. So the higher the concentration, the greater the number of collisions. The greater the number of collisions, the more likely you're going to have a reaction, and vice versa. So we're going to express our rates in what's called a rate law or a rate expression. I'm going to keep referring to it because I'm used to it calling it the rate law. So the rate law, the rate expression, and it's going to look like this. It's going to say the rate is going to be equal to some number with units, and we'll talk about how to figure that out as part of this video. Some number, K. Now that K is going to change. Its K is going to be different for different reactions, and that K is going to be different for different temperatures. Okay, so that is just a global catch-all that allows us to go from the units of concentration to units of rate or speed, how fast the reaction is going to go. And we'll talk a little bit more in a second about how this looks very, very different. So for the reaction that we have of the dinitrogen pentoxide reaction that we saw in the last video, that rate law looks like this, where the concentration is directly proportional to the rate. Meaning, if I double the concentration, I'm going to double the rate. If I triple the concentration, I'm going to triple the rate. And it's all going to get multiplied through by some little number. So that K is called the rate law constant. Okay, it is independent of the quantities, but it is dependent on what reaction is taking place and what temperature that's happening. So another way to look at that is generically, if I have this ultra generic A plus B gives you C, then the rate law is going to take the expression, take the appearance of rate equals K. K is your rate law constant times the concentration of the first reactant raised to some power times the concentration of the second reactant raised to some power. And what's going to happen is for every single reactant that is part of the reaction, you're going to have this power that you're going to raise your concentration to. In our previous example, that constant was a 1. Okay, for this particular rate law, the constant was a 1, which meant concentration doubled, you double the rate. Concentration tripled, you triple the rate. But it can be any whole number. It can be any whole number, 0 on up. So the rate laws have to be determined experimentally. There is no way for you to look at a reaction, especially if you do not know the mechanism, and we'll talk about that later on as like the last section we'll do. If you don't know how the reaction takes place, how the molecules collide, then, and all you know is these two reactants come together, then what you're going to have to do is experimentally determine what the rate law is. And the way we do that is we test. We take the concentrations and we change them for each of the reactants and see what it does to the speed of the reaction. The lab that we were going to do with this unit did a fantastic job of explaining or showing how this comparison takes place, how this relationship takes place, and how sometimes it's more aggressive and sometimes less. But you have to determine experimentally. You can't just stare at a reaction and say, oh, that's what that is. So what do those exponents mean? Well, they're called the orders. When you have that number that is the raise, the power, that is called the order. So the first type of order is zeroth order. So if that number is a 0, if that number that's up top is a 0, that exponent is a 0, what that means is that the rate does not depend at all on the amount or the concentration of that reactant. Think about it. If I have a rate law that says rate equals K times A to the 0 power, well, any number raised to 0 power is 1. Any number raised to 0 power is 1. So what that means is the rate is straight up all the time, no matter what, whatever that K value is. No matter what the concentration is, the rate is going to stay the same. So if I double the concentration of something, it is not going to have any impact whatsoever on the rate of the reaction. That is a 0th order reaction. Well, what if it was 1? Well, we already saw what happens there. If that exponent is 1, that's called first order. And for first order reactions, what you have is this direct proportionality between, if you increase the concentration, I'm going to increase the rate at the exact same order, exact same amount. So if I double the concentration, I'm going to double the rate. If I triple the concentration, I'm going to triple the rate. If I quadruple the concentration, I'm going to quadruple the rate. Whatever you do is proportionally a direct proportionality between whatever change you make on the concentration, that same exact change is going to happen on the rate. And think about it, if you double, say you go from 1 molar to 2 molar, the difference is 2 molar. So 2 raised to the first power is 2. So you're going to double the rate. And the rate law looks like this, K times A raised to the first power. And then the last order is second. Now, there's a lot of orders past second, and they're not very common. And again, when we get to rates, maybe that'll make a little more sense. But let's just say the most common orders of reactions are 0, 1, and 2. There are thirds, fourth, fifth, sixth, so on and so forth, but they're super, super uncommon. And again, when we get to rate law, we get to mechanisms, we'll explain why that is and what has to happen in order for a reaction to take place that has a higher order. So if the exponent is, or the order is a 2, that means it's second order, which means you have a slightly different proportionality. You have, if I double the concentration, then I'm going to double to the second power. I'm going to double to the second power, or quadruple the rate of the reaction. So these are reactions where the order is so aggressive that as I increase the concentration, I'm not just going to double the concentration, I'm going to make it quadruple. And you can imagine if this order was third, it'd be 2 raised to the third power, or it'd be multiplied times a factor of 8. Big differences. So as the orders increase, the impact of changing the concentration of that reactant significantly increases. So let's look at the way this works. Now, what probably, and again, I'm going to say this as a quick aside, as far as this chapter goes, what we're going to discuss today is probably the skill that's associated with this chapter. Being able to look at data of a reaction rate, and be able to look at what happens to a reaction over time or at initial data, and determine what order the reaction is. So we're going to do that for initial rate data. So what we're going to do, and this is what it looks like, is we're going to take a reaction, nitrogen monoxide plus hydrogen to give you nitrogen and water, and we're going to do this multiple times. We're going to do this reaction multiple times, but we're going to keep changing the concentrations of the reactants. So you'll notice trial 1, we made both of them 0.1 and we got a rate. And then for trial 2, we decided just to change the hydrogen concentration. So we doubled the hydrogen concentration and we wanted to see what happened to the rate. And then we went back and said, well, now we knew what happens when we only change the hydrogen concentration. What happens if we only change the nitrogen monoxide concentration? And we did that also. So let's analyze this data. Okay, so look, first off, what you're looking for when you're analyzing this data, or data like this, is you're looking for trends. So what I notice here is that as I double the concentration of nitrogen monoxide, and this is the key, while making sure the concentrations of everything else stays the same. Okay, let's look at this. Between trial 1 and trial 3, I've doubled nitrogen monoxide. But this is the important part. I keep the concentration of everything else the same. Between trial 2 and trial 3, I also doubled the concentration of NO. But in that situation, between trial 2 and trial 3, the hydrogen did not stay the same, so I cannot use those two pieces of data. So I go and I know that nitrogen monoxide has doubled, while everything else stays the same, and then I analyze. So what happens to the rate? Well, as it rate doubles, the rate quadruples. Okay, let's look at that. My rate here, it quadruples. Okay, it goes from being 1.23 times 10 to the negative third to 4.92. You do the math, that's a factor of 4. So as my nitrogen monoxide doubles, while everything else stays the same, my rate quadruples, which means, since concentration ratio, this is the way I like to look at it, the concentration ratio, I doubled my concentration. 2 raised to what power? I don't know what that is. 2 raised to what power is my rate ratio. So 2 raised to x is my rate ratio is 4, it quadrupled. So you should be able to do the math in your head that 2 raised to 2 is 4, which means this reaction is second order with respect to nitrogen monoxide. And then what you have to do is check it out again and find out what order it is with respect to hydrogen. So we're going to look at the data again, and we got to find 2 trials where hydrogen doubles and nitrogen monoxide stays the same. Which 2 trials are we going to use? Hopefully you said we're going to use trials 1 and 2, because as you go from trial 1 to trial 2, the hydrogen concentration doubles while the nitrogen monoxide stays the same. And what happened to the rate? Well, if we look at that, we realize the rate has doubled. So as hydrogen doubles, the rate doubles. As the hydrogen concentration doubles, the rate doubles. So again, doing the same thing, concentration ratio raised to the order is the rate ratio. If I double the concentration, and that doubles the rate, 2 to what power is 2? Well, that's going to be 1, or first order. So this rate law has a appearance of rate equals K times NO to the second and H2O to the first. Well, the last thing you got to do is figure out what the heck K is. We have to now figure out what K is. So I need to just take any trial. It doesn't matter. If you do this correctly, it absolutely does not matter which trial you take. So I'm going to take the rate law equation, solve it for K, and then plug numbers in. I took the first trial. The rate was 1.23 times 10 to the negative third molarities per second. My concentration of nitrogen monoxide was 1.1, and I'm going to square it because it is a second order with respect to nitrogen monoxide. And then 0.1 to the first, and I do that math, I get 1.23. That's what I get if I do the first trial. But the key here is just to be persistent. It doesn't matter which trial you choose. If I choose the first trial, I get 1.23. If I choose the second trial, I get 1.23. If I choose the third trial, I get 1.23. It doesn't matter which trial I choose. Now let's talk units. Units are a little tougher. Okay, notice the units are molarities to the negative second, seconds to the negative 1. That means if I take just my units here, molarities per second, and divide them by molarities squared and molarities to the first, I'm going to get molarities to the negative 2, 2 molarities in the bottom, and a seconds in the bottom, which means my units are molarities to the negative 2, seconds to the negative 1. Okay. I'm going to go ahead and pause this video and start to try to download it. And then I'm going to come back with a second video that is going to allow us to go through some more examples. So hopefully everybody's having a good day. I'm going to just start getting this downloaded, and then we're going to try one more time to do a couple more examples, including the one that's on the screen.